Good evening. Thanks so much for coming. I'm delighted to introduce to you Alexander Rehding on his first visit here. This evening we have the great privilege to hear and talk with an exceptionally imaginative and wide-ranging thinker about music, sound, and culture, whose range of concerns and writings spans an immense range, from ancient Greek and Egyptian music to the classics of the Western repertoire, to Chinese music, the Eurovision Song Contest, music and climate change, even music launched into outer space. Educated at Cambridge University and a native of Hamburg, Germany, Alex is Fanny Peabody Professor of Music at Harvard University. There, he was part of a group that reorganized the study of the humanities and also co-chaired the committee that made fundamental changes to the undergraduate study of music, opening its curriculum to those who came to it for a very different background. So you can get a sense of him. He spent a sabbatical year learning ancient Greek. So you can see he's actually a Johnny, too. Let me read you some of the titles of his writings. Music Historical Egyptomania, 1650 to 1950. The Quest for the Origins of Music, circa 1900. The Discovery of Slowness in Music, with John Mackay, Music Theory and Platonic Dialogues, and one of my favorites, Rousseau, Rameau, and Enharmonic Furies in the French Enlightenment. He has co-edited 5 big volumes that are wonderful monuments of collaboration, and his books include the following: Hugo Riemann and the Birth of Modern Musical Thought, Music and Monumentality, Commemoration and Wonderment in 19th Century Germany, Beethoven's Ninth Symphony, and his latest book with Daniel Chua, Alien Listening, Music from Earth and Voyager's Golden Record. His talk this evening is entitled Sounding Alarm, circa 1850. Please welcome Alex Rehding.
Thank you so much for this warm introduction, and thank you so much for the invitation. It's really wonderful to be here. As Mr. Pesek said, it's my first time in Santa Fe, and I'm very excited to be here. After hearing about this wonderful place from Mr. Pesek and various other alums that I'm friends with, so it's very special to be here. And I have to say special thanks to Mr. Blackmar and Mr. Forrest and Ms. Romero, who helped organize this trip. And I want to start with a crib sheet, because I know that you all study music, but not all of you may be musicians. And I just wanted to very quickly, flash the parts of music and sound and the construction of tones that are going to be important in this talk. It will all come back, so don't worry too much if you have questions. And if it comes up, you have this crib sheet in your hands and you can look it up when, if anything is confusing. So the first thing to know is that the fundamental difference between musical sounds and non-musical sounds is typically given in the nature of the sound wave, that musical sounds have periodic vibrations, they have regular patterns. Noise is typically defined as non-periodic vibrations, and I've just given you some examples here. And when you look at the sound wave, there are typically at least 3 musical dimensions that are correlated with elements of the sine wave. The amplitude, gives you an indication of the loudness. It's not always one-on-one. It gets a little more complicated, but we don't need to worry about any of those details here. Then the frequency gives you information about the pitch, the height of the tone that you hear. And then the third dimension is the waveform, the shape that the period has, that gives you some information about timbre, about the quality of sound that helps you identify, say, a trumpet sound and a violin sound, and that tells you what the difference is between those two. So those are the 3 main dimensions that we need, that we will encounter today. Then there are a couple of other things. You probably, I know you've all played around with monochords, which is great. And then you will also know that the basic intervals of Western music and several other musical systems around the world are correlated with simple integer ratios, so that the octave corresponds to a string length ratio of 1 to 2. The next simple interval, the fifth, corresponds to 2 to 3, then 3 to 4 is the fourth, and so on. And that's been known for a very long time. Another thing that people noticed, starting in the 17th century, noticed in a scientific sense, they wrote about it, is that when you play a complex sound, on a string instrument, on a cello, you hear one pitch, one fundamental tone height, and then there are lots of other things going on that at the time they called petits sons, little sounds. And as it turns out, these little sounds, we would now call them harmonics or upper partials, or even overtones, are in those ratios of 1 to 2 to 3 to 4 to 5 to 6 and so on. And so they sound the basic intervals. And so on, it continues. And you can even demonstrate how this works on the piano. If I press down silently some of the upper partials, and then I strike really loudly the fundamental, then we should be able to hear the upper partials ring out. I'm not sure if you'll be able to hear that from all the way back there, but I'll give it my best shot. So that's kind of a demonstration of how upper partials are in the sound wave, even though we don't typically hear them as individual components. But that's going to be one of the important parts. Okay, so all that is just preamble, and now I'll start. Let's see, I just have to get my right sheets here. Okay. The 19th century was a noisy time. Philosophers like Arthur Schopenhauer complained bitterly about how street noises interrupted their thoughts and made philosophizing impossible. And Henry David Thoreau even chose the seclusion of Walden Pond in Massachusetts to get away from the bustle of civilization. This century of industrialization is characterized by such noises as steam engines powering material progress, trains noisily chugging across the continent, the bangs and booms of increasingly sophisticated firearms, and factory whistles dictating the rhythm of daily life. Even music, in many ways the opposite of noise, seems to become noisier, as numerous caricatures from that time point out. Within the world of sound around 1800, everything seemed A-OK. When the German physicist Ernst Chladni published his groundbreaking book, The Acoustic, in 1802, it was such a smash hit that Napoleon himself agreed to pay for the French translation of the book. There was a palpable sense around 1800 that Chladni had gotten to the bottom of acoustics, that we finally knew what a tone was. And that was very reassuring. Chladni was well known for his demonstration that made sound visible. For this, sand was scattered on a metal plate that was then set in vibration by means of a violin bow. And here we see a contemporary illustration. And you will have noticed that we've set up some science demos. For now, if there is time after the talk and you're not too tired, we can play around with these. I think I have everything on video, which might be a little easier, but I definitely want to try out some of those classic experiments with you. And so the grains of sand on this metal plate would collect in the parts of the plates and form symmetrical patterns depending on the modes of vibration. The illustrations in Chladni's book, The Acoustic, outlined a number of these possible patterns. And here we see these rather beautiful patterns that really enchanted readers at the time. They became known as sound figures or Chladni figures, patterns that were created by sounds out of thin air and that gave a certain permanence to the normally evanescent sound and made it visible. One of the things that fascinated Chladni's romantic contemporaries above all was the fact that it showed the wonder of nature without destroying it by means of numbers and scientific analysis. Instead, it brought out the inner voice of nature, as it were. This was the kind of romantic science that they aspired to. And here we can see someone doing that demonstration in the traditional way with a bow. If I remember correctly, it starts rather suddenly and it's not the most pleasant noise. So let's see how it goes. So he's given us quite a few of those Chladni patterns, and he's much better at bowing the plate than I am. I'm not a string player, and I tried it, and I just can't do it. So Chladni's age knew that musical tones, that is, sounds with a definite fixed pitch, were based on standing waves. And there were essentially two ways of setting up standing waves, either by means of a vibrating string, as in a violin, guitar, or piano, or by means of an air column inside a closed or open pipe, as found in woodwind and brass instruments. All musical sounds were based on the regular vibrations of a periodic, regularly recurring waveform. By contrast, all non-musical sounds, that is noise, were based on irregular, non-periodic vibrations. So far, so good. Things were very clear-cut, everything had a certain beauty and elegance. But only a few years later, the unthinkable happened. A new device was invented that seemed to disprove the certainties of Chladni's acoustics. This new device, which was first presented to the public by the French engineer Charles Cagnard de la Tour in 1819, was fittingly called the Siren. As a French speaker, he was thinking primarily of mermaids here, since his device, la Sirène, could work underwater as well as in the air. But the overtones of the classical sirens, especially the seductive kind that Homer describes in his Odyssey, were appropriate too, since the siren served to lead the metaphorical ship of acoustic science off course and brought it in danger of capsizing. One detail that I rather like in this is that Homer, if you remember that passage, that famous passage from Book 12, Homer gives us zero information about what the sirens look like. It is as if they have no body. They're just pure voice. And I don't know if Cagnard picked up on this, but it definitely becomes important in this discussion. So this is how the siren works. Air is blown in from below by means of a bellows, and that sets a metal disc in vibration. And we can best see it in the view from above. We can see how holes are, this is a metal disc, and holes in regular intervals are cut into the siren. And if we look at the cross-section below, we can see that the bores of the disc are diagonal. And underneath that disc, that metal disc, is another metal disc with diagonal bores in the opposite direction. And so there are two identical, or very similar discs with holes in the same places, but with diagonally opposing bores. And of course, what happens when the air is blown in from below is that it presses against the upper disc, and the disc starts rotating. And each time, the two of the holes coincide. An air puff gets out, and the disc moves on. And as the top disc moves faster, it gets propelled around. And there are two things that happen. When the disc starts moving, we hear a series of air puffs, of pulsations. This is very, very soft. When you read the description of it, people like to use words like explosions or shocks or things like that, but they're really very soft. It's very hard to hear this in real life. And then when the top disc starts spinning at a certain speed, what we would now call 20 hertz, something different happens. Instead of hearing that pulsation, we hear a pitch, and the pitch rises depending on how fast the disc moves. Right. So, the siren was a very special kind of instrument that, contradicted the previous mechanisms of sound generation, whereas conventional instruments tended to work in a kind of regular sine wave. The siren produced a sound that was really a starting and stopping, a series of on and off clicks or shocks. Oh, what happened here? I'm sorry, I pressed the wrong button. And now I've lost everything. Maybe I'll try that again. Yes, it came back. Thank God for that. Okay. Here we go. Here's my diagram. So conventional musical sound basically always works in a form of sine wave. This is the simplest possible version of it. Whereas the siren seemed to follow a different pattern. It seemed to be a kind of on-off succession. And people didn't really know what to do with that. It was a real head-scratcher for the physicists at the time. And the siren was explicitly designed to put into question the theories that Chladni and others had established. As Kanyar explained, he had set out to ask the following question. If, as physicists believe, instrumental sound is principally based on the regular succession of multiple impulses, or shocks is the word that he uses, passed on to the atmosphere by means of their vibrations, it seems only natural to think that with a mechanism put together so as to stir the air with the same speed and the same regularity, one could give rise to sound generation. In other words, Kanyar wanted to create a device that would simply set the air in motion without the help of a traditional musical instrument. It wouldn't be wrong to think of the siren as a non-instrument, a device that, like Homer's ancient sirens, had no sounding body, unlike the conventional musical intervals that all tend to fall in the general strings or wind category. And it turned out that the siren worked, and it worked in a rather specific way. When the siren turned slowly, as we just said, the impulses were audible as individual air puffs, and when it speeded up, the individual pulses would fuse into one continuous tone that would gradually rise in pitch. And this is what it sounds like. And I should just insert here, in case you're wondering, how does this relate to the modern siren, the alarm siren that we now know? It's the same principle, essentially, but the alarm function that we now know about siren only became possible around 1905 when sirens became electric. That was the first time that they had enough energy to produce a really, really loud sound. As you can hear, this is not loud at all. And so throughout the 19th century, the alarm function was carried out by church bells. And so this only happened much later. I have all sorts of fun anecdotes about this, but we can talk about those later. Everybody who experienced the siren was amazed that this object could create a musical sound, specifically a continuous musical sound that was created out of discontinuous impulses, Kanyar's shocks. It violated the traditional principle of natura non facit saltus, nature doesn't make leaps, that guided traditional natural philosophy and appeared explicitly in Leibniz, Linnaeus, and even Darwin. This principle explicitly denied the possibility that a continuous sensation could emerge out of a discontinuous stimulus. So what was going on here? Researchers generally made 4 observations that they found baffling. First, continuous perception out of discontinuous stimulus. That's exactly what we were just describing here, the principle of natura non facit saltus. And that would be a philosophical crisis. And then the next question, a little more specific, is the Chladni question. Is the old wave model really still tenable? That would be a scientific crisis. And then one other really interesting point that musicians cared about deeply was that the category boundary between noise and musical tones was far less clear-cut than they had anticipated. And so we can call that a conceptual crisis. And finally, pitches and rhythms are not clearly distinguished. We think of them as distinct musical parameters, but as the Siren demonstrated, they exist on a continuum. And so we could call that a perceptual crisis or even a cognitive crisis. And for a while, it really seemed as if all the certainties of Chladni's theories were destroyed. Chladni himself may have been the first to admit that his scientific theories were not fully tenable in light of the Siren and needed to be refined. So he wrote in 1826, "From all this, we can see that the notion of tone should be taken in a broader sense than we generally do, in which standing waves of a sounding body are not strictly necessary, but rather impulses in rapid succession of any kind that are communicated through the surrounding medium to the ear." Other commentators saw this chaos as an opening for a new theory and perhaps a new kind of music. The anonymous reviewer in the Neue Zeitschrift für Musik in 1855 offered a poetic paraphrase of the experience of the Siren that turns it into a magical and in some ways outright erotic experience. And I'm going to give you a long quotation now, but I think it's worth it. "In the center of a large, darkened room, there is a rod, which under certain conditions is set to vibrate. And every care need be taken that the vibrations are in regular succession and that their velocity can be continually increased. I step into the dark room at a time when the rod makes but few vibrations. Neither ear nor eye tells me anything about the presence of this rod, but I feel it's vibrating. My hand can sense its throb when it touches the rod. The vibrations become faster. They reach a certain number and now I perceive a noise. It is individual beats or thumps that I can discriminate with my ear. Small explosions whose rapid succession I can barely follow. The vibrations of the rod increase relentlessly. The explosions follow one after the other in more and more rapid succession. They become ever stronger. There is one moment where my ear cannot discriminate any longer. In my mind, they merge into one. I only perceive a whirring noise, and suddenly a low bass tone strikes my ear. It is of such stunning intensity that no other sound, not my voice, not a musical instrument, not even the sound of an organ, could be heard at all. This tone continually rises in pitch. It passes through the entire medium range up to the shrillest high-pitched sound that pierces our ear with unbearable intensity. But now everything falls back into dead silence. Still astonished by what I heard, I suddenly feel a pleasant warmth radiating from the very point where just now the siren died away, as cozy as a fireplace. But everything around me is still plunged into darkness. Meanwhile, the vibrations become faster still. A weak red light emerges. It becomes more and more intensive. The rod is glowing. First red, then it turns yellow, then blue. It passes through all the colors until after violet, everything sinks back into the night. That is the siren of our century, which in its characteristic effect can well measure up to the one that once lured Odysseus. Of course, this image of a throbbing siren that traverses various senses and reaches into what's effectively the microwave range was nothing but a fantasy. And I tried really hard to find a model of such a siren, but I've been unable to locate anything even remotely related. And in reality, as we know from experiments at the time, it was impossible to crank a siren fast enough to reach the top end of the audible range. And here's a little fun side story. The reason you hear this musical background, some of you may have recognized it as the opening of Wagner's Ring, the Rheingold Prelude, is because this this article was originally published anonymously, but the following year it was republished, and the author put his name to it. It was Richard Pohl, who is a progressive music critic at the time and a card-carrying Wagnerian. He was a member of the Inner Circle, and he even signed his reviews with Opelt as a foot soldier for the Wagnerian cause. And in reading this description of the Siren that becomes ever more intense, it's hard not to think of this music of the Rheingold Prelude, which Wagner was writing at exactly the same time. We cannot prove that there is a connection, but it's a very nice link. But in any case, this is merely a side note. What I'm really interested in here are the questions that the Siren raises for music and the crisis that it caused. And I should be clear here, this was absolutely fundamental. It was a crisis of knowledge, an epistemic crisis, but it was also a crisis of very limited scope. The years that I'm interested in here, the 1820s to the 1860s, were the decades in which some of the most beloved music in the canon of European art music was written. This time period covers such important works as Beethoven's Ninth Symphony, Schubert's Winterreise, Berlioz's Symphonie Fantastique, Verdi's Rigoletto, or Wagner's Tristan and Isolde. So we can say with some certainty that composers weren't intimidated by this crisis of confidence, and in fact, most composers weren't even aware of it. But the crisis manifested itself in other ways. Crisis, meaning judgment or decision, is a situation in which old certainties are no longer valid, when the old hierarchies are toppled and others may become established. It's an unstable time, a period of trial and openness in which anything seems possible. And this is what I'm interested in here. Where might music have gone? And a synonym that's often used instead of crisis is crossroads or junction, and that's why it shows this image. This spatial image of the crossroads conveys that there is a fork in the road and that we have to make a decision to take one path or the other, just like Hercules here. There are a few alternative trajectories for music that were conceived at the time and that imagined a very different musical future. The names that we're going to encounter here are not found in music books or in most other histories, but they're no less fascinating, and it's rarely a bad idea to spend a minute thinking about the things that might have been. So let's start with one of my favorites, Wilhelm Opelt. Wilhelm Opelt is the most important music theorist you never heard of. He was a civil servant in Saxony. He was a jack of all trades in applied math. His day job was mostly in tax collection, but he had extensive mathematical hobbies. He's mostly remembered nowadays for calculating the size of lunar craters along with his son. But he also spent his spare time developing a pension scheme for his home state of Saxony. He translated an important mechanics textbook from the French, and he dabbled in music theory. And he is so unknown that there's not even a picture of him available on the internet, and you realize that's saying something. But we do have a picture of the lunar crater that was named after him and his son, so I'm going to use that here instead. He was fascinated by the demonstration of the Siren and the lessons it had to offer. And so he even developed his own Siren, and he wrote 2 music theory treatises, based on the Siren and what it meant for music. And for Opelt, the realization that both pitch and rhythm are located along the time axis was the most mind-boggling aspect of Cagnard's experiment. He zoomed in on that issue and asked if the 2 parameters, pitch and rhythm, can be correlated in more rigorous ways. And for an answer, he built his own Siren, a much more complex model than Cagnard's simple design. His Siren allowed him to play multiple tones at the same time. And the answer that his multiphonic Siren offered was a clear and resounding yes. Pitch and rhythm are correlated in interesting ways that music had not properly pursued. So here's what Opelt found. The Siren can create multiple tones in 2 fundamentally different ways that are indistinguishable to the ear. It can either blow air over 2 independent parallel circles for holes, for instance, one circle with 20 holes and a second one with 30 holes. And these two rows will sound the interval of the fifth in the ratio 2:3. And the pitch will rise as the wheel speeds up, but the interval between the two pitches will always stay constant. And the second way to create the same interval is to merge the two circles into one. And this is the really interesting part here. So this looks very forbidding, but it's much less scary than it looks. We'll just look at the simplest of these polyrhythms, 2:3. So you remember that ratio is the ratio that corresponds to the interval of the fifth. And this is in the top part here in the diagram. And so in order to sound the interval of the fifth, we can either have two parallel circles that sound independent, and one would be in triplets, and the other would be in duplets. And when I play both together, it's something like this. And so I can have them on independent circles in parallel, or I can put them on one circle as a compound rhythm. And so that would basically be if I didn't use both of my hands to tap out this rhythm, but just used one hand. And so on. And so this compound rhythm is the ratio, it represents the ratio 2:3. And in the bottom diagram, which is taken from his treatise under number 15, he has spatialized those rhythms. And so you can see the line between two big dots with three little dots in the middle. And if you take this as a time axis, then it really is just the same as the rhythms. Dum, ba, da, dum, bum. And so if you then go to the circle here, you can see that the circle that you see complete is nothing but four versions of this top pattern laid out in a circle. So if I start at 12 o'clock, then what we have is dum ba da dum bum bum ba da dum bum bum ba da dum bum and so on. So this is the compound rhythm of 2:3, and he's absolutely right. It does sound not one pitch, but two at the same time, and they are a fifth apart. So you can create one complex pattern of holes in order to create two sounds at the same time. And you can do that with any level of complexity. So he lays out 3 to 4 and 4 to 5. In the outermost circle of his very complex Siren disc is the compound rhythm of a full four-voiced chord, which is in the ratio, I think, 4 to 5 to 6 to 8. And so it's a pretty complex pattern, polyrhythmically speaking, and it does sound multiple tones at once. And so, the same, and we observe the same phenomenon as with Cagnard's siren, that when it turns slowly, what we hear is a sequence of air puffs. Now they're irregular air puffs, and when it speeds up, the sound fuses into pitches, and in this case, it's more than one pitch. And so we have a demonstration of this, so let's see. Here we go. This is a rather wonderful Italian series where they really take their historical experiments very seriously. so on. Opel's idea about music theory took this realization and ran with it. He started systematizing it. In his idea, all aspects of music should be unified. Pitch and rhythm and beyond that form, they should all be based on the same patterns and repeat themselves at different levels. And in computer science, this would be called recursion. The only problem here is there is no music that works this way. The idea is completely overdetermined, and it really wouldn't be very interesting music. The best we can look for are momentary effects in music that make use of this idea. And even then, there are really very few examples in the musical repertory, and I tried to look very hard. So here are 3 examples that I could find. The first one is the American experimentalist Henry Cowell, who probably comes the closest to what Opelt has in mind. He wrote a youthful composition called Quartet Romantic, that's not very well known, in which he composes for 4 solo instruments, and the pitch, they all play different pitches. The pitches are relatively uninteresting, and it's probably unfair to say they're irrelevant, but the principal interest here is that each of the instrument plays in a different pulsation. And so we have this idea of ratios at the heart of the composition. And so, what it really does is the whole composition is a 4-voiced Bach chorale style composition that's not played as chords, but as rhythmic relations. And so it's sort of, stretched out so that the ratios are not heard as pitches, but as rhythms. So just to give you a very quick example of the opening sonority, we have pulsations in sextuplets, quintuplets, then 4 notes per bar and 2. So in terms of ratios, if we look at the harmonic series, that is the 2nd, 4th, and 5th partial of the complex sound, which is a major triad with the fundamental, with the root in the bass doubled, with the octave below. And so, basically the whole piece spells out 4-part chords like this as rhythmic relations. I'll give you the first couple of bars, I think. No, that didn't work. Let's try that again. I'm sorry. Oh, this will take forever. Okay. Sorry, we have to go through all of this again. Okay. No, we should. No, I must have. Oh, I'm sorry. Well, it's not a great composition. Other than that one piece from the early 20th century, the idea only really started coming into its own in the context of electronic music, in this case, electronic dance music. I found 2 more examples. This is by Moby, a track called 1000 that made it into the Guinness Book of World Records because it's the piece with the fastest beat ever recorded. What happens is that it speeds up the basic beat of his piece. It starts out at a relatively normal speed for electronic dance music, and it gets faster and faster until it hits 1,000 beats per minute. 1,000 beats per minute is 16.6 beats per second, so 16.6 hertz, which is almost at the auditory threshold, right? So when it cranks up all the way to the end, you're on the verge of hearing it as a pitch and no longer as a rhythm. This could be quite loud. It's sort of a pretty nasty sound. We'll see how it goes. This is the beat. at the end, you can sort of get a sense of how it is almost a pitch. It's sort of, not a very nice timbre, but you can, it does fuse. People who are really into electronic dance music don't like this track because it's so gimmicky, and there's probably some truth to it that he mostly wrote it in order to get into the Guinness Book of Records. The classic example is Stockhausen's electronic piece Kontakte, which does exactly the opposite. We first hear a sound that's quite, that we hear as a fused sound, and it meanders downwards until it hits the auditory threshold, goes below 20 hertz, and then it starts sounding as a pulsation. It becomes slower and slower. And here's the graphic score. Let's see if you can follow it. I think it's relatively straightforward, hopefully. A few other sounds to start with. There we go. There we go. Now, the crucial part here is that these composers didn't know about one another or about Opelt. They all thought they had a fully original idea, especially Stockhausen, who wrote about how he went to the Swiss Alps, to the solitude of the mountains, and that's where he had this insight. And then his colleague Herbert Eimert said, actually, no, there is this guy called Opelt. But all these examples are in different genres. There is really no overlap. When I put them next to each other, it's very hard to construe a historical trajectory out of them. And Opelt was virtually unknown to all of them. There were two influential music critics in the 19th century, François Fétis from Belgium and Gottfried Weber from Vienna. They were sent a copy of Opel's book and read it and reviewed it, and they were impressed, but they also said this has virtually no chance of becoming mainstream. And they were right. But let's move on to a different musician who is my second hero in this story, who was also deeply affected by the mid-19th century crisis of sound. Jean-Georges Kastner, or Johann Georg Kastner, was an Alsatian musician and scholar, so he lived in that borderland between France and Germany. He was raised German-speaking, but then went to Paris Conservatory and became a French composer. And then he did something smart. He married rich and didn't have to work for a living. And so as a gentleman of leisure, he spent most of his life inventing a new literary genre and then he perfected it. And he called it the livre partition, the book score. And this genre included a treatise on a big theme from the cultural history of music, such as Dances of Death, or the psychological powers of military music, or the soundscape of the city of Paris. And it was always followed by an original composition by him on the same topic. And we know that these compositions weren't exactly bestsellers. A review from 1910 states that none of Kastner's works had ever been performed. And as far as I can tell, nothing much has changed in the century since then. And that's not because they were bad. They are really quite good compositions, I think. But getting performed was really not a priority for Kastner. The specifications for the orchestra are often extraordinarily demanding. I mean, there is one passage in his symphony, Les Cris de Paris, where he requires 40 sax horns for just, 8 bars. And the sax horn, I don't know how many of you know that instrument. It was invented by Adolf Sax, who also invented the saxophone. That's one that stuck, but the sax horn did not stick. And I'm not even sure if 40 sax horns were ever, produced existed at the same time. But Kastner was completely shaken to the core by Cagnard's Siren, and he acutely felt the crisis. And his particular problem was, if the siren annihilated our entire understanding of the nature of sound, then maybe we needed new and better models. And he was particularly concerned with what we called earlier the conceptual crisis of music, that the division between noise and musical sound should be so porous that there was no longer a clear-cut divide between noise on the one hand and musical sound on the other. But this is where our noisy 19th century comes in. The period in which Kastner was working was an age of many new inventions. And musical instruments were no exception. The pages of Kastner's books are brimming with the marvels of newly invented instruments driven by fire, steam, gas, water, or even electricity. And none of these instruments have survived, and the pyrophone, a kind of fire organ, that enjoyed some years of popularity until one of them exploded during a concert. But these new instruments give a vivid picture of the possibilities that the disappearance of the old certainties opened up. And within it, Kastner's search for a new, more robust definition what a musical tone might be. And in this quest, Kastner placed high hopes in a curious instrument, the Aeolian harp. And so here we see a rather nice demonstration of how the Aeolian harp works. It's really just a box, often a wooden box, with a more like a zither or lyre kind of arrangement of strings. It's typically between 3 and 12 strings. They're all the same length. They're all the same tension. So they should all sound the same, but they don't. And it's also not an instrument that's plucked or played by human hands, but it's played by the wind. Aiolos, wind in Greek. And so here we can see how it works. The wind blows into that chamber and it stirs somehow magically, mysteriously the strings, and very strange sounds come out at the other end. Nowadays, the Aeolian harp is rather unknown, but it really was the darling of the generation of Romantic poets. Coleridge, Shelley, and the German poet Novalis were among the many who addressed the ethereal Aeolian harp through poetry. And as I just indicated, despite the name, it's not really a harp, and it really doesn't sound like one. Far from it. So here's an example. What fascinated the Romantics was obviously that the instrument plays without human interference, and that it's the wind that produces the music. How exactly it worked was a total mystery at the time. At the time Kastner was writing, there was no physical explanation of how the instrument worked and how it produced its sound. There were several theories, going back to Athanasius Kirche in the 17th century, as most things do, but none hit the mark. It was not until the early 20th century that we found a theory that physicists can agree on. And as it turns out, the sound is not produced by the strings themselves, but rather by turbulences that occur behind the strings, and they're called von Karman vortexes. What particularly fascinated Kastner about the Aeolian harp was that it was so unstable in all the dimensions of sound. It vacillated between melody and harmony. It sounded dissonances, simultaneous and successive. Its bass note wobbled, it crescendoed and decrescendoed, and its timbre was constantly changing. At a time in which all that was solid had melted into air, it's easy to see how this musical object that seemed to be sounded directly by nature might hold the key to what musical sound might actually be. Now, Kastner's treatise is full of transcriptions of the Aeolian harp, but you can sense his frustration at just being able to capture partial aspects of this otherworldly sound. And so he finally includes a new composition at the end of the treatise that presents a full simulation of the Aeolian harp for no less than a double orchestra. And I would love to play you this example, that simulation, but as I said, Kastner's works have never been performed, so I can only show you the score. And I'm just going to dazzle you with the score. You don't have to worry about any of the details, just to note how finely graduated the dynamics are. Then in the strings, you see all sorts of special effects with harmonics and mutes. And it's really, of a complexity that you don't see in the 19th century. You don't really see, that level of extended techniques well into the 20th century. And I would say there is a certain resemblance to spectralist scores. But in any case, in this transcription, the whole massive orchestral apparatus is needed to recreate one single timbre, the enigmatic sound of the humble instrument that is the Aeolian harp. In light of the chaos that the Siren had sowed, Kastner became convinced that looking at notes and tones wasn't good enough, that he had to zoom in further, more closely. And a new music theory that would come to terms with the true reality of music, he felt, had to start with the subatomic particles of tones, the building blocks of musical sound, whatever they might be. And that's the reason why Kastner became very interested in string harmonics, the throaty high sounds that string instruments can play by partly stopping the strings at nodal points. At Kastner's time, there was no physical explanation of how they were produced. Even though Kastner's own speculation on how these harmonics came about was not accurate, he was still generally on the right track. And as we now know, the related phenomenon of upper partials or overtones are in fact the building blocks from which more complex timbres are formed. In fact, at exactly the same time, in the 1850s, physicists were discussing this very question, how complex sine waves could be broken down into smaller components. And the application of the mathematical technology of Fourier analysis provided the answer. Now, Kastner's book shows no awareness of any of these discussions, but Kastner's instincts were good. He intuitively grasped that harmonics must be part of the answer. There's a certain irony that Kastner's speculations had in fact very little to do with the actual way the Aeolian harp worked, but in some ways, the chief function of this instrument had always been to provide inspiration to romantic minds, and Kastner really was no exception here. If anything, it seemed that the kind of instrument that Kastner was thinking of that could wobble in all dimensions was the additive synthesizer. And it becomes pretty clear that this is what he has in mind when he describes, what he wishes the Aeolian harp was about. So, the additive synthesizer was experimented on a little later. Helmholtz presents a prototype in the 1860s, but it doesn't really get going until the 1890s, early 20th century. And in that, with that electronic instrument, the dimension of timbre was, set free as a musical dimension in its own right and gave rise to 20th century electronic music. Now, we could conclude this paper with the landmark publication of Hermann von Helmholtz's treatises on the sensations of tone of 1863, which effectively solved the mystery that Cagnard's Siren had opened up some 40 years previously. However, putting it that way is not quite correct, because the mystery had been solved a little earlier by the physicist Georg Simon Ohm, who had been embattled with his colleague August Seebeck over the precise significance of the siren. Seebeck, who was an experimental physicist, felt that the siren had disproved the traditional theories of sound, whereas Ohm was sure that the old theories were solid, just in need of refinement. And he finally found the refinement he needed in the mathematical technique of Fourier analysis, which has now become a major part of acoustics, and especially the dimension of timbre. Most of what Helmholtz did was to use his gravitas and his stellar international reputation as a platform to promote Ohm's theories. And here's what Ohm found in a nutshell. He argued that we should imagine the siren not as a series of individual clicks in on-off succession, but rather as a wave with a flat maximum and a flat minimum part. That was a much more complex, we would now call that a square wave, right? It's sort of part of the standard repertoire of electronically generated sounds. But it was a much more complex sound wave than anything we'd seen before. But, and this is the crucial part, it was still essentially a kind of sine wave, and Fourier analysis helped him calculate it. Problem solved. Now, in most accounts, this resolution is seen as a redemptive moment, a breakthrough for science that led music out of an awkward impasse. Crisis averted. But that's not quite how I see it. In some ways, knowing the right answer is the end of all other possibilities. The crisis, deeply unsettling though it was for those affected by it, was a moment in time at which the creative minds, the imaginary wizards, the ones who had faith in a bit of magical thinking, pointed the way forward. And as we saw, what they said wasn't necessarily completely correct, but it also wasn't completely incorrect. It's best to think of our thinkers like Opelt and Kastner as soothsayers pointing out a different trajectory that would have led into a different musical future. As Winston Churchill is reputed to have said, never let a good crisis go to waste, though he probably didn't say that. This approach to thinking about history, which emerges out of this crisis, as I've outlined here, is sometimes called counterfactual history or alternate history. There is an element of it here, but it's not exactly counterfactual. Everybody I discussed here today really existed. It's just we know their works had very little historical impact. The only counterfactual element here is the weighting of events. If we take our starting point from Kastner or from Opelt, we will foreground rather different historical trajectories, grounded in different priorities. The alternative futures that emerge out of Opelt and Kastner's writings allow us to forge new connections across the pantheon of musical works. They give us a fresh perspective. And sometimes it's not a bad idea to leave a bit of noise in our retellings of the noisy 19th century. Thank you very much.